This is the third module of chapter 7. In this module, we will discuss two particular type of integral domains. One we call Euclidean domain and the other is known as principal ideal domains. In the Euclidean domain, we will show that there are some integral domains where there is a division algorithm, and the integral domains in which every ideal is principal are known as principal ideal domain. Recall that our known integral domain, the ring of integers, possess these two properties. Recall that in the introduction of this chapter, I told you that our motivation of this chapter is to generalize some basic properties of the ring of integers. So, in this module, we will generalize division algorithm and the fact that every ideal of Z is principal. First, we define Euclidean domain. Let E be an integral domain. A function v from E star to Z hash, where E star is the set of all non-zero elements of E and Z hash is the set of all non-negative integers, is said to be a Euclidean valuation on E if for all a b in E with a non-zero we have two elements q r in E such that B can be expressed as a q plus r, where either r equal to 0 or V r is less than V a, and valuation of the product A B is always greater than equal to valuation of A for all non-zero A B. An integral domain E together with a valuation V on E is called a Euclidean domain, and it will be denoted by the pair E V. Recall that we have division algorithm in the ring of integers and on the polynomial ring over field. In case of integers, the division algorithm is such that B equal to a q plus r, where either r equal to 0 or r is greater than 0 and less than modulus of A. And in case of polynomials over a field f, we have f x equal to g x into q x plus r x, where either r x is the 0 polynomial or degree of r x is less than degree of g x. So, the valuation is actually generalization of the absolute value in case of ring of integers, and in case of polynomials it generalizes the degree of a non-zero polynomial. And in all these cases, recall that the absolute value of an integer is always non-negative and degree is also always non-negative. That is why here we have taken the valuation function v from E star into Z hash, that is Z hash is the set of all non-negative integers, and valuation is taken only on E star, not on E, because we cannot define degree of the 0 polynomial. So, the ring of all integers Z is a Euclidean domain where valuation is taken to be the absolute value. Also, the ring of all polynomials over a field is a Euclidean domain since every non-zero polynomial gx has a unit leading coefficient. So, we always have fx equal to qx into gx plus rx satisfying this condition, and since valuation is taken to be the degree, all the conditions of valuation is satisfied. Now, we have a very interesting result that if E is a Euclidean domain with valuation V, then every unit in E have the same valuation as 1. Actually, we will prove that valuation of A is equal to the valuation of 1 if and only if A is a unit in E. First, assume that A is a unit, then there exists an element B in E such that AB equal to 1, which implies that valuation of 1 is equal to valuation of AB, and by the second axiom it is greater than equal to VA. Thus, V1 becomes greater than equal to VA. Also note that for any A in E star, VA is equal to V1 into A, which is greater than equal to V1. Thus, it follows that VA is equal to V1. For the converse, assume that A is a non-zero element and valuation of A is equal to the valuation of 1. We are to show that A must be a unit, that is, there is some Q such that 1 equal to QA. Since A is non-zero, by the first axiom of the definition, we have two elements Q and R in E such that 1 is equal to QA plus R, where R equal to 0 or VR is less than VA. Since we have assumed VA equal to V1, it follows that VR is strictly less than V1, but it is impossible since always VR is greater than equal to V1. This contradiction arises because we have assumed R to be non-zero. So, we must have R 0, and thus 1 becomes equal to Q into A, and hence A is a unit. Now, we show that every field is a Euclidean domain. In view of the above result, it follows that every non-zero element of F must have the same valuation as the valuation of 1. So, here the valuation function must be constant, and it can be proved easily. Any value in Z hash can be taken to be the valuation of the elements in F star. Thus, we have the field of complex numbers, the field of real numbers, and the field of rational numbers, all are Euclidean domains. Now, we define principal ideal domain. Already I have defined principal ideal ring, that is a ring in which every ideal is a principal ideal that is generated by a single element. So, naturally the definition of a principal ideal domain will be an integral domain in which every ideal is a principal ideal. You know that the ideals of Z are of the form Nz, that is generated by some n. In other words, every ideal of Z is a principal ideal, and hence Z is also a PID. And in the 5th chapter, I have proved that if Fx is a polynomial ring over the field F, then every ideal is a principal ideal, and hence the polynomial ring over a field F is a principal ideal domain. Just now we have proved that Fx is a Euclidean domain and we already have Fx is a principal ideal domain. Here I will prove that actually every Euclidean domain is a principal ideal domain. Consider a Euclidean domain EV and an ideal I. We are to show that I must be a principal ideal. If I is the 0 ideal, then it is generated by 0. Assume that I is a non-zero ideal. Just like the proof of the result that every ideal of Fx is a principal ideal, here also we will use the well ordering principle to prove that the ideal I is a principal ideal. Note that to prove that I is a principal ideal, our main problem is to identify an element in I which is potential enough to be a generator of I. For this I will use well ordering principle. So, consider a set n of all valuations of x where x is a non-zero element of I. Since I have taken I to be a non-zero ideal, there must be a non-zero element in I. So, n becomes a non-empty subset of the set of all non-negative integers, and hence by the well ordering principle it has the least element. Assume that A is a non-zero element in I having the least valuation V A, that is V A is less than equal to V x for all non-zero x in I. We show that this A is a generator of I, that is we have to prove that I is equal to E A, that is every element of I can be expressed as a multiple of A. First note that since A is in I and I is an ideal, we have E A is a subset of I. For the converse, that is reverse inclusion, assume an arbitrary element B from I. Since E is a Euclidean domain and A is non-zero, we have two elements Q and R in E such that B is equal to AQ plus R, where R is either 0 or valuation of R must be strictly smaller than valuation of A. We will actually show that R must be 0. If possible, assume that R is non-zero. Then R equal to B minus AQ, and since B and A both are in I, so we have B minus AQ is in I, that is R belongs to I. And if R is non-zero, then valuation of R is less than valuation of A, which contradicts the minimality of V A. In other words, contradicts the choice of A, that we have chosen A to be an element in I having the least valuation. So, we must have R 0, and so B becomes equal to A into Q, that is B becomes an element of E A. Thus, I is a subset of E A, and ultimately it follows I is equal to E A. We have a very interesting result which characterizes the polynomial rings R x which are Euclidean domain. Here we show that a polynomial ring f x is an Euclidean domain if and only if f is a field. Note that we have proved already that if f is a field, then f x is a Euclidean domain, and just now we have proved that every Euclidean domain is a principal ideal domain. Thus, the implications from 1 to 2 and 2 to 3 already we have proved. Here it remains to prove only that 3 implies 1. So, assume that f x is a principal ideal domain. We show that every non-zero element of f is a unit. So, consider an arbitrary non-zero element A from F. Here the given condition is that f x is a principal ideal domain. So, I have to use the fact that every ideal of f x is a principal ideal. For this, consider an ideal I which is generated by A and the indeterminate x. This is an ideal of f x. Since every ideal of f x is principal, so we must have some u x in f x such that I is generated by u x. Now, both A and x are in u x implies that we have some g x and h x such that A is equal to u x into g x and x is equal to u x into h x. Since f is an integral domain, u x into g x equal to A implies that degree of u x must be 0. That is, u x is a constant polynomial. In other words, u x is equal to some b in f, which implies that b into h x is equal to x. If we compare the coefficient of x in this identity, we get some c such that b c equal to 1, where c belongs to f. Thus, b becomes a unit, and note that b is actually the generator u x of I. So, I becomes the whole ring f x, and thus 1 belongs to I, which implies that 1 must be expressed as a combination of a and x, that is 1 is equal to a into some f 1 x plus x into some f 2 x. Again, if we compare the constant terms of this identity, we get 1 as a multiple of a, that is a becomes a unit in f. Since a is considered as an arbitrary element of f, an arbitrary non-zero element of f, it follows that f is a field. Here we are discussing the integral domains in which every ideal is a principal ideal. So, it is my duty to give an example of an integral domain where there are ideals which are not principal, because we already have 2 examples which are principal ideal domains. Now, I will give an example which is not a principal ideal domain. Actually, from the above theorem, it follows that the polynomial ring Z x can never be a principal ideal domain, because Z is not a field. Still, I would like to exhibit here example of an ideal which is not principal. If you consider the ideal generated by 2 and the indeterminate x, then similar to the proof in the previous theorem, you will get some c such that 1 is equal to 2c, where c is in Z, but it is not possible. Hence, the ideal generated by x 2 can never be a principal ideal. Now, we discuss about the existence of GCD in Euclidean domain and principal ideal domain, and relation between irreducible elements and prime elements. Recall that in a principal ideal ring, if A, B are 2 elements not both 0, then GCD of A, B exists, and if D is a GCD of A, B, then D can be expressed as A u plus B v. Since every Euclidean domain is a principal ideal domain and every principal ideal domain is also a principal ideal ring, so in a Euclidean domain given two elements A, B not both 0, GCD AB exists. Also we have, if D is an integral domain, then every prime element in D is irreducible. Here we show that if D is a principal ideal domain, then the converse also holds, that is every irreducible element is also prime. So formally we can state that suppose R is a Euclidean domain or a principal ideal domain, and AB are two elements of R not both 0, then A and B have a GCD D in R, and for every GCD D of A and B there exists ST in R such that D equal to SA plus TB. And also we have AB are relatively prime if and only if there exists ST in R such that one can be expressed as SA plus. Now we show that if R is a principal ideal ring, then every irreducible element in R is prime. Consider an irreducible element P in R. To show that P is prime, assume P divides AB. Then AB is equal to PC for some C in R. Now we show that either P divides A or P divides B. For this, consider the ideal generated by PB. Since R is a principal ideal ring, there is some D in R such that the ideal generated by PB is also generated by D. Thus P belongs to the ideal generated by D, and hence there exists some Q in R such that P is equal to DQ. Since P is irreducible, either D is a unit or Q is a unit. If D is a unit, then the ideal generated by D becomes the whole ring R, and hence 1 belongs to ideal generated by PB, that is 1 becomes SP plus TB for some ST in R. Multiply A to both sides and it follows that P divides A. If Q is a unit, then D becomes Q inverse into P, and hence D belongs to the ideal generated by P. This implies that ideal generated by D is a subset of ideal generated by P, which again a subset of ideal generated by PB, which is equal to ideal generated by D. Thus ideal generated by P becomes equal to the ideal generated by PB, and so B belongs to the ideal generated by P, that is P divides B. Thus either P divides A or P divides B, and hence P becomes prime. Since in an integral domain every prime element is irreducible, thus it follows that in a principal ideal domain, which is an integral domain and at the same time a principal ideal ring, we have an element P is irreducible if and only if it is prime. Now note that in Z we have only the notion of prime integers. There is no idea of irreducibility, and the definition of irreducibility and prime element coincides in Z. This is because of this result, since Z is a PID, there the irreducibility and primality coincide. Recall that if R is a ring and an ideal generated by Q is maximal, then Q is irreducible, but the converse does not hold. Here we show that if R is a principal ideal domain, the converse also holds. That is, if R is a principal ideal domain, then M is a maximal ideal if and only if M is generated by some irreducible element. Here assume that Q is an irreducible element and the ideal generated by Q is denoted by M. To prove that M is maximal, suppose there is an ideal I of R in between M and R. Since R is a principal ideal domain, there exists an element A in R which generates I. Then Q belongs to the ideal generated by A, and hence Q is equal to A into B for some B in R. Since Q is irreducible, we have either A is a unit or B is a unit. If A is a unit, then the ideal generated by A, that is I, becomes equal to R. Now we show that if B is a unit, then I is equal to M. If B is a unit, then Q equal to AB implies that A equal to Q into B inverse, that is A belongs to the ideal generated by Q, that is ideal M. This implies that ideal generated by A, that is I, is a subset of M. Also we have M is a subset of I, and hence M and I are the same. In a PIR, we have a result that an ideal P is prime if and only if it is generated by a prime element. So, if R is a principal ideal domain, since in a principal ideal domain the prime elements and irreducible elements are essentially same, so a proper ideal P of R is prime if and only if it is maximal. So, in Z, since Z is a principal ideal domain, the prime ideals and maximal ideals are the same, which are of the form Pz, where P is a prime integer.
Roll.
Thus, we have an explanation why the prime ideals and maximal ideals in Z coincide. In this module, we have discussed Euclidean domains and principal ideal domains, especially the special features of the principal ideal domain, which are generalizations of Z, just like the prime elements and maximal elements in the principal ideal domain coincide. GCD of two elements not both 0 exists in PID. Bezout's identity holds in PID, and also recall that a polynomial ring Fx is a Euclidean domain if and only if it is a principal ideal domain, and which is equivalent to F being a field.